All right, folks, I can speak louder, perhaps you don't need a microphone for the few words that I have to say before we start here. So this the distinction lecture series for the new emeriti. And before we start with the introduction, with the laudation and the presentation, we are going to have a slideshow that I would like that you pay attention to that. Let's welcome and celebrate distinguished Professor Alan Balch for his 56-plus years of service to the University of California. Let's start with Alan Balch's professional genealogy, which was created by Drs. Vera Mines and Greg Girolami. Alan was on Greg's PhD committee when Greg graduated from UC Berkeley in 1981. Alan Balch's professional genealogy shows that he was wired for worldwide chemistry collaboration, said Katie Hunt, former president of the American Chemical Society, 2007. And Alan shaped so many careers. Here are some examples. Congratulations, Alan, and thank you for taking me on as a student and sticking with me as a lifelong mentor, colleague, and friend. Give Paula a hug for me. Being a graduate research advisor was only one of the things Dr. Balch did for me. He is a coach, cheerleader, strong believer, and listener. I'll treasure the memories and lessons learned and carry them with me always. Wishing you joy, success, and continued inspiration in all your endeavors. Farewell, and thank you again. It was an honor to be a postdoctoral researcher in Alan Balch's group at UC Davis. During my time in his lab, I contributed to several impactful publications, an experience that shaped my career as a researcher and educator. Alan's brilliance as a scientist and his mentoring dedication continues to inspire me in my work as a professor at the National Changhua University of Education in Taiwan. Congratulations, Alan, on your extraordinary career and profound legacy in inorganic chemistry. Congratulations. Thank you for giving me the foundations to learn, teach, and parent with the grace and patience you've shown to all of us over the years. Hi, Alan. I was a postdoc in your lab from 2001 to 2004 and worked on the heme degradation process. You are an excellent scientist and great mentor who provides complete freedom and a pleasant lab environment. It was a wonderful and memorable experience for me academically and personally, shaping my life completely. I do not doubt that whatever I am today is only because of you. Thank you and Paula for everything you did for me. My family joins me in wishing you and Paula a wonderful life ahead filled with love, happiness, and good health. We are all very proud of you and your achievements. Thank you once again. Thank you for taking the risk of having me as your graduate student. You are my academic father, a lifelong mentor, and a career coach. I would not be where I am without you. Congrats on your 56 years of contribution to the inorganic chemistry field, and enjoy your retirement. Congratulations on reaching emeritus status. I'm so grateful for your guidance over the years, and I know you will continue to make meaningful contributions to all the communities you are part of. Alan, as you transition to emeritus status, this is a time to celebrate and reflect on your extraordinary journey and the enduring legacy you leave behind. Your career has been a shining example of excellence, characterized by an insatiable pursuit of knowledge, a profound passion for chemistry, and an unrelenting curiosity about the world. You have been a guiding light, inspiring and empowering countless students to confidently navigate their academic and professional paths. The lives you've touched and the minds you've shaped are enduring testaments to your remarkable influence. Your dedication, wisdom, and unwavering support have enriched this institution and the individuals fortunate enough to learn from you. Being your student was an absolute privilege and joy. I will always cherish your infectious excitement at every result, insightful guidance on every experiment, and unique ability to craft compelling narratives around every project. These lessons extended far beyond chemistry, profoundly shaping careers and lives. With deep respect and heartfelt gratitude, I celebrate this well-deserved milestone with you and wish you every happiness and success in this new chapter of your life. Raising a pint to toast your retirement and an amazing career. Your professional dedication and contributions continue to inspire. Cheers! Dear Alan, I admire and respect how hard and successfully you've worked over your long scientific career. You not only made a huge difference, but also touched a lot of lives along the way. Happy retirement, Leszek. Hello, Alan. I want to express My deepest gratitude for your incredible impact on my personal and professional growth. Your unwavering excitement and passion for science were contagious, and I learned to incorporate this into my career. Your wisdom and mentorship have been instrumental in shaping my career and personal growth. Thank you for being an incredible mentor. Congratulations, Alan. I wish I could be there to tell you this in person. I remain thankful for all your guidance and support over the years. Dear Alan, I am so grateful to have you as my mentor, both professionally and personally. Thank you for encouraging me to pursue my passions, and please keep doing what you do beyond retirement. Alan, you weren't just an advisor, you were a rare gem who connected with students on a truly human level. Researching with you was a joy, but the greatest gift was the kinder, wiser perspective on life I gained from you. I wish you endless joy ahead, surrounded by laughter, family, and unforgettable moments with your grandkids. Alan Balch at the ACS meeting in 2020. This photo is courtesy of Joel Miller, Alan's first graduate student at UCLA. Thank you, Alan, for being an inspiration to the UC Davis faculty.
Thank you.
And now we invited to the podium distinguished Professor Susan Kautzerlich for a laudation of Alan Balch. Susan.
Great. Well, let's see. It's my pleasure to give this laudation for Professor Alan L. Balch. I've known Alan personally since 1989 when I met him at UC Davis. However, I was already well aware of his research before I actually met him in person, because I had read his publications on one-dimensional metals, chain complexes, and his work on binuclear complexes of platinum and palladium. He was already well known as an outstanding synthetic chemist, and I came to Davis because of his reputation, along with that of Phil Power and Marilyn Olmsted. Alan earned his BA degree in 1962 from Cornell University, and he must have possessed a passion for research already at that stage, as he was co-author on 2 papers with his undergraduate advisor, David Guss. He was recognized as an outstanding student, receiving a Leeds and Northrop Fellowship, as well as an NSF pre-doctoral fellowship. He was inducted into the Phi Beta Kappa, one of the oldest and most prestigious academic honor societies. His first paper appeared in the premier journal of the American Chemical Society, which we all know as the Journal of the American Chemical Society. He then attended Harvard for both his master's and PhD under the guidance of Richard H. Home, who we all know as Dick Home. He maintained high productivity, and he published 7 papers in the top-tier journals in the field of chemistry. Began his career at the University of California system in 1966 at UCLA. He moved to UC Davis in 1970 and became an associate professor in 1972, full professor in 1977, and a distinguished professor in 1994. He served as chair of the Department of Chemistry from 1994 to 1997. His research and contributions to the field have been acknowledged by several prestigious honors, including the American Chemical Society ACS Fellow, an American Association for the Advancement of Science AAAS Fellow, the ACS Award F. Albert Cotton Award in Synthetic Inorganic Chemistry, and an NSF Creativity Award. He's delivered lectures at various named symposia, both in the United States and internationally. He served as an associate editor for the Journal of Inorganic Chemistry from 2006 to 2021, and has been on numerous editorial advisory boards. Before discussing his research, I want to emphasize some of his service to the university. So as I mentioned, from 1994 to 1997, Alan served as chair to the Department of Chemistry at UC Davis. During this time, extramural funding grew to $17 million portfolio by the end of his time as chair, even though the prospects for research support were bleak nationwide. Undergraduate enrollment surged to 14,000 students. He involved our faculty in the redesigning of both the organic chemistry and general chemistry courses to improve course offerings for this large influx of new students. 6 new faculty members were added to the department under his watch, partially replacing the 11 faculty who retired prematurely due to the VERA program in the early 90s. As chair, Alan collaborated with the molecular and cellular biology department to successfully establish a core group of faculty in macromolecular X-ray crystallography. Recruitment in the field of structural biology posed particular challenges involving 2 departments across 2 colleges, joint search committees, 2 department chairs, and 2 deans. At the time he was doing this, it was like a very novel idea that we would collaborate across, especially across colleges. The addition of faculty in the macromolecular X-ray crystallography had been the topic of discussion in UC Davis for over 20 years, and Alan played a key role in establishing this research core. Alongside the successful recruitment of 3 faculty members in structural biology, he contributed to a successful proposal to the Keck Foundation, securing an additional $1 million for the university to enhance equipment and facilities for structural biology. So this was a time of great change for the department, for the College of Letters and Science. When Alan started, he was reporting to 3 different deans, Deans Crummy, Tomlinson Kesey, and Rock. Alan participated in an advisory committee, and a transition occurred from the College of Letters and Science to the Division of Mathematical and Physical Sciences within the College of Letters and Science. This model proved successful for chemistry and the college for 25 years, and during this time, this transition, Alan strongly and effectively opposed the addition of a 4th Uber Dean for college administration. Alan has led the inorganic chemistry in our department, helping those faculty in our department to become a powerhouse in inorganic chemistry, recognized nationally and internationally. He has been and continues to be our inorganic chemistry graduate advisor, and his commitment to diversity, equity, and inclusion has profoundly shaped our department and graduate student body. He has established a research environment in his own lab that appeals to a diverse group of individuals, as you've seen in the video, including undergraduates, graduate students, postdocs, visiting faculty members. And many PhD students graduating from the Balch group have been women and members of underserved groups. Students from his lab have gone on to hold leadership positions in industry and academia, including the past president of the American Chemical Society, Katie Hunt, an ACS award winner, Joel Miller, and a former UC Davis vice chancellor, Fred Wood, among others. He has also leveraged his excellent relationships with the Cal State University campuses to recruit the diverse population of graduate students into the graduate program at UC Davis. In particular, when he was the chair of the graduate recruitment committee. So it's accurate to say that his efforts have helped transform the makeup of our graduate students into a diverse body that better reflects the demographics of California. Alan has had a highly successful career, publishing over 550 peer-reviewed articles. His research interests are broad, encompassing biochemistry, coordination cluster chemistry, as well as materials chemistry and electrochemistry. His papers appear in, I think, the whole spectrum of journals that cover chemistry. And his research is characterized by both breadth and depth, emphasizing the synthesis, structure, and bonding of new complexes and materials. Alan has achieved international distinction in Fullerene chemistry, discovering new compounds that in many cases were unimaginable until they were structurally characterized. These compounds have shown potential in technological applications, including redox, active thin films for batteries, microelectronics, coatings, and magnetic resonance imaging agents. In addition, his work on structure, chemical bonding, and reactivity of a diverse array of metal complexes constitutes significant fundamental advances. In the Fullerene field, he's been at the forefront of fundamental breakthroughs in understanding structure, bonding, and chemistries of these novel clusters. In the metal cluster field, his group led to a remarkable discovery and research, solvoluminescence. These are clusters, trimers of gold complexes that release bursts of light upon contact with a solvent. In the metalloporphyrin field, he's made significant contributions to our understanding of the coordination capabilities of iron porphyrins. Of course, I could go on for some time just trying to capture the essence of his research contributions, but I would like to just say a few last words before we get this lecture started. Overall, Alan Balch embodies the quintessential image of a distinguished professor in the UC system. He's an exceptional colleague, highly innovative, a remarkable researcher leading a robust fundamental research program that has significantly impacted the field. His work has provided essential knowledge and understanding of the potential structures, properties, and chemical reactivity of these exciting new polymorphs of carbon. His advances in cluster chemistry have resulted in new structurally elucidated compounds with novel properties. And probably even more importantly, he's been an outstanding mentor to students, postdocs, and to the faculty, especially the junior faculty and inorganic division. He's training the next generation of leaders for the chemistry community. My dear colleagues, students, and Professor Balch's lab alumni who are here, join me in welcoming distinguished Professor Alan Balch to the podium.
I'm overwhelmed and take a minute to get my composure together. Thank you all for coming. It's a real pleasure to see so many of you and actually recognize some of you and have some people here that I don't recognize who I presume are students. And so I'm here to, maybe I'm going to teach you a little chemistry and maybe not. We'll have to see how that goes. Let's get on with looking at these slides. There's the title. I'm going to give you some history of what the campus was like when I got here. And then I'm going to talk about some projects. We're going to talk about molecular oxygen and how that gets activated. We'll talk about molecules and crystals. We'll talk about Fullerene crystals, and we'll talk about reactive crystals. And the best part of this talk really comes at the end when we have some films showing you reactive crystals and things that they can do. So hang around to the bitter end, and it should be interesting. Okay. You've seen this picture before. This is my research group shortly before COVID hit. And I'm really, this group is very important to me because it was difficult getting through COVID. And these folks that really helped me survive. And I'm forever grateful to every one of you. A few people that I should point out. This is the late Professor Marilyn Olmsted, who is has been a constant contributor to research projects in my group. I'll say a little bit more about her a little bit later. And the folks over here, Sarah, and Anna are people who joined my group subsequent to this photograph, and so they ended up on the post over there. Yeah, the really wonderful thing about working with students, and I've worked with graduate students and upper division undergraduates all my career, and they never really get old. They don't age. They graduate and then new set of students comes along. And so forever working with young people. And I think that keeps you young. And I've really appreciated the opportunity to work with these people. So let me go from there to a little bit of history, and I'm going to do that via a map. I like maps. I hope you can endure this map. Let's see, where's my pointer? There it is. This is the chemistry building. So this is the center of my universe. And my pointer, will the pointer behave? Well, let's see. You should be able to see the Shields Library is up here in the upper right corner. And okay, here's the silo area. And over here's an important building, Gowsey Hall, in this lecture. So when I came, there were sheep in the silo. I think they lasted about 2 years or so, but the silo was a sheep barn at one time. After that, I could park right in front of the silo area. It was an unpaved area. There were no parking fees. Parking on campus was free with little supervision of things. And yeah, it was a smaller campus. I mean, I think we had 14,000 students all told on the campus when I came here. Let's see, and over in Gowsey Hall, that was a hog barn. And I used to have to walk past that if I parked and walked in for a large part of my career. And if I had visitors, we had to walk past the hog barn. And the hog barn just was not a pleasant place. It had the smells, and it had flies and mud. And yes, so we were all glad when Gowsey Hall got built. And then finally, in the chemistry building, we had typewriters, but I didn't know how to type. So I wrote my papers on legal pads with a number 2 pencil, and then gave them to my secretary, who then typed up the paper, and I would then distribute it to people. And when I distributed it to people, I got back comments like, I hope your secretary makes up in speed for what she lacks in accuracy, which really is a reflection on my own inability to proofread, because I let this thing go out without checking it over very carefully. Other things that went on at that time were publications. We got publications as like this, as magazines, and they came in the mail, and some of us had subscriptions. Other times we'd go over to the library and pick these up. But yeah, this was a real, I mean, I still like this sort of thing. It's really very nice. This particular issue is particularly important because this is the first time anybody in my department got a picture on the cover of, this is the only journal that had pictures on the cover at those days. So this was really a pioneering thing. And the picture that you have here was constructed by Ella Fung Jones, who's sitting right there. And you heard about this solvoluminescence phenomenon. Unfortunately, I didn't plan to talk about that today, but this is light coming from crystals when solvent hits them. And we'll see a little bit more about that a little bit later on. Okay, so that's what I remember. Let's go on here. So when I came here, the inorganic department consisted of Ken Musker and the late Jim Swinehart, and they welcomed me. Marilyn Olmsted was here, but she was acting as a lecturer in the general chemistry program. So I'm the white space in here. And then the next hire that we made in inorganic area was Gerd Lamar, who's in the audience, but I can't see him. Oh, yes, there's Gerd right up there. Gerd came and was a really welcome addition because he brought skills in NMR spectroscopy to us, and then developed the UCD NMR facility. After that, we hired Phil Power, who's also here. And these people now are both retired as I am. And then we started hiring other folks. We hired Susan Kalsworth, who you just met, Dave Britt, who's over here, Frank Osterloh, Luis Bourbon, Jesus Velasquez, Marie Heffern, and the most recently, Bronte Charette. So those are, and you can see the group has grown, which is a nice thing to see the faculty size increase. And it's a really nice group. We get along, I think, pretty darn well. And we have a lunch once a month, and remind us that the lunch is coming up this Friday. But it's been a real treat to work with these individuals. We also had another aspect of the department. When I came, Håkan Hoppe was our crystallographer, and he started a tradition of crystallography within the department that's continued. Marilyn Olmsted became a professor eventually, but when I came, she had not published anything. And her research advisor felt it was more important to write papers with men rather than with women. That's that recently. She eventually became a postdoc with me, and I'm kind of happy to say that her first publication, I'm a co-author on that publication, and from that she came up with this idea that she would learn crystallography, and so Håkan and I supported her for a year or two while she learned crystallography. Then she eventually became, after serving as postdocs and helpers, she became our staff crystallographer, and then eventually became professor of chemistry. At one time, and this may still be true, she was the most highly cited female scientist in the country. When she became full professor, we needed somebody to replace her, and so that's Dr. Jim Fettinger, who's here in the audience, and he's currently continuing. And then we had produced a number of our students. This is Cameron Ghiazzi, who has gone on also to continue a career in which X-ray crystallography plays a big role. So I'm very pleased to have this group behind me. So I'm going to tell you about a few projects. The first project is a molecular oxygen activation. O2 is around us, 20% of the atmosphere is around us. It supports combustion, but we don't burst into flame, right? You have to do something to make oxygen reactive. And that's what we decided to study. We did this in conjunction with Gerd Lamar. We did this using mostly nuclear magnetic resonance spectroscopy. And I'm not going to show you any NMR spectra. We're really going to simplify this chemistry terrifically. But what we worked with were hemes, which is this molecule right here. The most important thing is the iron right in the middle. That's the only thing I really care about. Well, I care about some more things as time has gone on, but that's where I started. And then you notice it's got 4 nitrogens around it, and then it's got this cyclic structure called a macrocycle. This is the compound that's responsible for the red blood, the red color in your blood, and it's responsible for picking up oxygen in your lungs and depositing it for use in your muscle tissue and throughout your body. At the bottom, a number of people who worked on this project, and many of them are from abroad. Derhan Chin and Ruzhen Cheng went back to get academic positions in Taiwan. Then there are people from Poland, there are people from Sri Lanka here, there are people from Switzerland, from Italy, from India, and I think that's about it. But we also had many foreign visitors who came to work on this project. It was a pretty good number of folks that went on to academic careers out of this particular group. So what did we do? Well, the chemistry is real. I'm going to show it to you in 4 steps. You take the O2 molecule, which has a really strong double bond between the 2 oxygens, and you bind it to iron, and you form a complex between the 2. That's what happens in your lungs. You're doing this right now. We're all doing it together. The next thing but that doesn't activate it. Nothing, that molecule is just transported around. To activate it, you have to do something else. And the thing that Gerd and I did was we took another iron and brought it up to contact this oxygen complex. And we did some chemistry there. At that point, we broke the double bond and we get this peroxo-bridged material. And that peroxo bridge is really weakened. We've started the process of breaking things down. And then the next step is that peroxide, under the right conditions, and we had to figure out what those conditions were, but under the right conditions, they broke apart and we made this ferryl ion. The ferrial ion is now a highly oxidized species, something we can go on and do chemistry with. And this was an important discovery that we made. Now, much of the chemistry in this project and in my lab today is conducted in the little tiny glass tubes that look like this. The chemists know that this is an NMR tube, but this also serves for crystal growth too. We'll see that a little later on. Anyway, we're doing this experiment, and two of my students, Leszek Laudation and I think Mark Renner, were over at the facility out here, the NMR facility, and they'd come out with samples. They had to keep the samples free of oxygen. They had to keep them cold because we all did all this chemistry at low temperature. And but they had to introduce chemicals into the top. And they'd come all the way from the chemistry building. So I had to plan pretty carefully to come out here and get this stuff in intact. Well, they were doing this, and the tubes are sealed much more carefully than this little plastic cap. And they have some syringes around, they have some chemicals, they want to introduce these things into the tubes. They're so excited about the experiment that they're shaking. They're shaking so badly that they're really having trouble getting this done. But eventually they did it, and the work got done. But I was just excited myself to know that my students were so engaged in the chemistry that they were that excited. Yeah. So let's see. Then, just to complicate matters further in this sequence, this last reaction is something you want to avoid, and yet you want iron 2 present. So you know there's a lot of care that has to be taken in how you carry out this chemistry. This took us about 10 years, I think, of the 26 years Gerd and I worked on this project. Gerd went on and looked at hemes in proteins and the position of the heme in the protein. And also we both started to look at heme degradation. You know, when you get a bruise, you get all kinds of colors. And that's being destroyed by oxygen in a controlled fashion. And so we studied that, and yeah, we learned an awful lot about it. Now, I repeated this slide because I want to tell you one more story. I got 2 phone calls from some kind of federal agency. I really want to know if anyone else has had this experience, but they wanted to know something about my research. And I was really excited about this because maybe they'll fund me, you know, this would be wonderful. So I made an appointment. They were going to, the first phone call, they made an appointment. I asked them, can I have a contact number to call you back? No, can't do that. And then but on the appointed day, the man shows up, and he's clearly out of place. He's got a dark suit on, he's got a tie, and his shiny black shoes are something to see. And he comes in, he asks me a little bit about my research, but then he asked me about somebody that's been in my lab. And what has this person done? What research has he done? And I actually gave him some papers that we had co-authored. And then he more questions about this individual. And then he said, did he travel at all, or did she travel at all? And I told them where the individual traveled, very interested in this travel. And yeah, and then left, and that's about all I can tell you about this encounter. It was all very mysterious, and yeah. Second time, similar situation. I made an appointment, didn't know how to contact people. This time, 2 people show up, and the issue in this case is really very specific. They don't want to know anything about my research. They want to know why one of the visitors to my lab was turned away by US officials at the border. And that was it. I was supposed to tell them this. And I had no clue. We had processed all the papers. The visa should have gone through smoothly, but this individual never actually got into the United States. Okay, enough with that story. Let's go on and talk about molecules and crystals. You all know about gemstones and hard crystals like this, emeralds and rubies, and that's not the kind of crystal that I'm interested in. For some reason, I never was interested in mineralogy, but I was interested in other kinds of crystals. But let me explain the difference. We'll start out with carbon. And we have over here on the left top the structure of diamond. And the idea is each carbon atom in diamond is tetrahedrally bound to 4 other carbon atoms. And there's a network of bonds that goes throughout the crystal. And that makes the diamond really tough, really hard, and it makes it colorless. And sort of not the sort of material that we're going to talk about here. Carbon also forms another form called an allotrope, and that's graphite. That's the stuff in lead pencils. Graphite is made up of sheets of carbon atoms, and there's strong bonding along those entire sheets. So chemical bonding there is very strong. But between the sheets, the interactions are weaker, and so the sheets can be moved about. They can be pulled off with a piece of Scotch tape. And this is a lubricating material. It's something that you can manipulate pretty easily. Now, there's also another form of carbon, and that's the buckyballs, which I got interested in. This is a case where now we're dealing with a molecular material. This is something that's soluble in organic compounds. It's highly colored, and it's got a unique and interesting structure, and I'll give you an example. This is a model not of C60, but of one with 70 carbon atoms. Each of these points is a carbon atom. There are 70 of these all told. And this is a molecule that has a discrete outside, and then it's got something on the inside. And the inside, chemists can work out here, but trying to do things on the inside is a whole nother matter. You can all see this. So these fullerenes come in different sizes, C60, C70, up to, well, C84 on this particular side. They're molecules. And when they form solids, they're going to form molecular solids. So let's talk a little bit about molecular solids. So we have this little rectangle that represents an individual molecule, strong bonds within it. We pack these together into crystalline solids with weak forces interacting and holding the molecules in place. And we can manipulate, as chemists, can manipulate those forces and do things with crystals. Crystals aren't just inanimate things. They're things that we can play with. But we can also use crystals to determine structure of molecules. And that's the predominant idea of using X-ray crystallography is let's find out what this molecule looks like. Let's visualize it in full 3 dimensions. A lot of structures. And some of the work that I'm going to tell you about is geared along that way. But, I put things together as you would put a row of bricks. There are other ways of putting those same molecules together. I can put them, sort of alternating, or I can put them right on top of each other. And those are different ways of crystallizing things, and we call them polymorphs. And a very common phenomenon in crystallography. And we have polymorph A and polymorph B, and they're just different ways of orienting things and putting them together. And then one thing that you notice here is that everybody is nicely in an organized array. Everybody's where they should be. Sometimes that's not true. Some molecules may twist themselves a little bit, and that produces crystalline disorder. And that's a real bugaboo in some of the chemistry that we do. There's also the possibility of, whoops, I went the wrong direction here. Let's go. We can also take 2 different substances, molecule A and molecule B, and we can form co-crystals. Co-crystals would look like this. I've got a layer of A-type molecules and a layer of B-type molecules, and then A and then B again. So you usually think about crystallization as a way of purifying things, but that's not necessarily the case. You can get molecules together. And there's an issue of what lets co-crystals form, and how can I manipulate this as a chemist? And that's one of the things that we've taken advantage of and made a living doing. So we're back to fullerenes, C60, this C70. And a typical co-crystal is this C60 with carbon disulfide in the crystal. And the problem there is that the little bricks weren't perfectly aligned. And so you get this jumble of things, which is a disordered crystal. And that's really hindered structure determination by X-ray crystallography and been a bugaboo that we've tried to avoid. And I'll show you some ways we've tried to avoid it. So we got interested in Fullerene chemistry. here was some form of carbon that hadn't been examined known about until 1985, and you have fundamental atom. And I came back to Davis after a trip to Illinois, and I knew that they had made some of this material. I knew it was purple, and I found that Phil and Susan had generated a little bit of C60 in the lab. And I convinced Vince Catalano, whose picture you saw earlier, to try to make some of it too. And Susan kindly let us use her equipment. We used it a few times. We broke it a few times, and we eventually developed our own way of generating. But if Susan hadn't been here, we would never have gotten to do this kind of chemistry. So what did we do? We took C60 and we took an iridium compound and we reacted them together in benzene, and crystals came out. And then it just formed spontaneously. We determined the structure of this molecule. This was nice. You can view this as forming a chemical bond between the fullerene and the iridium. It's sort of a weak co-crystal too, because in solution, everything's on the left side, and only in the solid state do we really get this adduct forming. We got that structure out, but the one that was really important is this one. This is this molecule, and we got an iridium compound. And we learned two things. This was the first time anything bigger than C60 had been crystallized and structure determined. And we found out that reactivity was up here, not on these flat sides, but up here where the molecule is most curved. Now, getting this structure was quite a job. Vince Catalano, who you saw earlier, and Jung Lee managed to grow the crystals, and we had nice crystals. We had a device called a rotating anode, a new X-ray generator that had worked for most of one day prior to this. We had a crystal that was going to take 7 to 10 days to collect data on. So Marilyn and Vince changed their vacation plans. A cot was brought into the lab, and Marilyn and Vince babysat the rotating anode for the entire period of time that we were collecting data. By the 5th day of data collection, we knew what the structure was. We started to write the paper. We still had, this would be about Tuesday, and the data collection is going to end up on Saturday. So we collect and we write the paper, and then on Saturday, we finally have the last numbers. We put the final digits in. I jump on my bicycle with a package of papers this thick, run down to the UPS store downtown, and we mail off the article. The rotating anode worked. It did its job, and I'm forever grateful for that. We're looking to buy a new X-ray diffractometer in the chemistry department. The claim is made that we can now get a structure in 18 minutes. So from 10 days to 18 minutes is pretty amazing. Okay, let's see. Oh, this picture graced the chemistry building walls for quite some time. This is my group of quite a few years ago. So there's an intersection between the porphyrin chemistry and the fullerene chemistry. We were taking this C60 oxide, C60O. We wanted to determine the structure, and we wanted to use the oxygen as an anchoring group. And we knew that there was a ruthenium compound, the one shown up there at the top, that had a similar type of structure. And we were going to set out to make that molecule. And we had everything we need. We could have done that, but we never got around to it. Instead, we used some cobalt porphyrin that we had around the lab. We knew that cobalt had an affinity for oxygen atoms, and we thought that, well, maybe cobalt will do it. We can do that in a hurry and not wait around to make a more complicated molecule. And it turned out we got crystals, and they're very nice crystals. But the most important thing about the crystals is here there's a clamshell. The two molecules of porphyrin surround the C60. And the C60 is perfectly ordered. There's no disorder in this structure. It's a really beautiful structure. And that then led to a utility of this in structure determination. You take a fullerene and you mix it with a porphyrin and you grow crystals, and the crystals invariably turn out to have a much better order than they would have if the porphyrin wasn't there. I started collaboration with with Harry Dorn and Steve Stevenson. We had a nice little article in Nature about some structures like this. And I'll show you a little bit more. It's possible to put, I said this thing was empty, but it's possible in the process of making these to have atoms go on the inside. And we've determined the structure of a number of molecules like that. And these are two that have pretty interesting things on the inside. The one on the left has 4 scandiums and 2 oxygens with a tetrahedral arrangement of scandiums. The one on the right has 3 oxygens and 4 scandiums. And these are little pieces of matter that exist inside the cage, but they have no existence in the chemical world outside of this. There's no gas phase chemistry of these units. There's no solid phase chemistry of these units. They're just entities that can be trapped because you have a cage that surrounds them. So we determined a lot of structures like this. And here's another one. This one is interesting. You know, round. It's kind of got an oblong egg-like shape, right? And that's because at the bottom, at the lower right, if I can get my pointer to work, yeah, right there, we have a violation of the isolated pentagon rule. We have 2 pentagons that touch each other, and that shouldn't happen, but it does happen here. So we get this kind of egg-shaped molecule that reminded me of a campus site. Why were we doing this? Well, at the time, these things are good MRI contrast agents. Tons of gadolinium are ingested into people for MRI contrast agents annually. These are very good contrast agents. The problem is we can't make enough of them. The yields of these syntheses of these compounds are just very, very low. But eventually, maybe we can find a way to make enough to do that. You've seen this picture of Brandon Mercado before, too. This is the largest cage that we've managed to discover, and I think it held the record for about maybe 15 years. There's a larger cage, about 108 carbon atoms, that's been discovered since then. And this is a picture of just these are many of the structures that have been determined by Marilyn and our students. Just a whole host of things. So I want to wind up with talking about some reactive crystals. These are Rochelle, White Morris, Sangho Lim, Lucy Luong, and then Stephen Grolinski, who's here in the audience, and Sarah Costa, who's here in the audience. And on the right is the picture of my favorite crystallization, I think. This is a big beaker with one gold compound in it. And there's ether and dichloromethanes in there. And you see crystals coming out, but there's not just one kind of crystal. There are clearly 2 kinds of crystals, one of which glows green under UV light, one of which glows blue under UV light. These pictures, many of the pictures you're going to see are taken under UV irradiation. So what's going on? How do we get 2 crystals out of one compound? Well, I showed you earlier, polymorphs, 2 different ways of arranging the same molecule within the crystal. And these are, we know what they are. And we know that they're gold compounds that form chains. One chain is linear, one chain is kinked. We also learned to grow, and here we are back to the NMR tube. These are 2 tubes. They're not NMR tubes, but they're about the same size. These are the glass tubes we use to grow crystals. And you can see that what we've got here is spatially controlled growth. We have green crystals growing at the top, blue glowing crystals forming at the bottom. And it's all due to a solvent gradient. We have dichloromethane, a good solvent at the bottom, diethyl ether, a terrible solvent at the top. Then the crystals are coming out in this fashion. Well, these crystals are reactive. This is a little movie I want to show you. This is a vapochromic situation. We've put, see if I can get this pointer to work again. Yeah, here we go. So put a long, thin crystal here. We put it in a container, and we put a volatile organic material, either methanol or dichloromethane or chloroform. And so that crystal this is the end that's closest to the a volatile material, and this is the end that's furthest out. and I'll just show you. This is sped up by a factor of 8. And watch what happens at the top. We're basically, the crystal is converting from the green glowing to the blue glowing form without changing. There's no vapor being taken up. These crystals are completely free of any organic solvent, and it stops. And it will stay like that for, well, we've documented it for a month. And the other important thing from our point of view is that this started out as a single crystal. It's a single crystal on the green end. It's also a single crystal on the blue end. So we've had a phase change take place in this crystal. And there must be something really interesting going on at the interface between these two. And I'm just not smart enough to know how to figure out and how to interrogate the crystal to find out what's going on. I'd like to see what the structure is, but I imagine it's pretty disordered in that interface. But that's something for someone else to study someday. So that's one kind of property. So, well, I have to do this twice. Yeah. So Lucy Luong, who did this work, was able to make crystals that had 2 components, like I showed you, 3 components, and even 4 different components, simply by taking one crystal and then exposing it to vapor at particular sites. And so we can make these really unusual things. They're crystals, but they have 2 different structures throughout their length. Well, we have crystals that are thermochromic, and that is they change. Let me see if I can get this to work. Here we go. So you don't see anything right now. There are crystals on that being immersed in liquid nitrogen. Sarah Costa made this picture for us. And you just don't see anything. They're colorless crystals, I think. Colorless or yellow? Yellow, okay. But now you see up in you can see the orange crystal starting to illuminate. There you can see it pretty well. So this is thermochromic. As you lower the temperature, it becomes luminescent. There's another kind of luminescence that we can see, and this is right here. Now we're back to that same compound that I showed you before, the long, thin crystals that I could make into 2-color or 3-color crystals. Same thing is going on here. We're going to heat this. Now we're starting out not with a green glowing crystal, but with a blue glowing crystal. We're just going to what's happening right now is the temperature is increasing. Temperature is constantly increasing, and something started to happen. It just started to happen where the plate was the hottest. And you can see what happens. It just goes through the crystal. The crystal maintains its shape, but it's no longer crystalline. This is not a single crystal, the single crystal transformation. It's a single crystal to amorphous material, but it's green glowing. And we turn off the light, and we're just going to continue. We're always heating. This is continuing to heat. And you're going to see what do you expect to happen as you heat a crystal? What's next? It's going to melt. And that's melting right there. And it just forms a molten blob. So that's that. And then, let's see. Okay. We also have crystals that are mechanochromic. That is, if we grind them up or we expose them to some kind of pressure, they undergo a change in color. So we start off with yellowish crystals on the left, and they become sort of reddish-violet crystals on the right. And in this process, the chemistry at the bottom shows what's happening. There's an SO2 molecule that gets released. Sulfur dioxide is a pollutant and also a useful chemical. But SO2 is released. And what's unusual about this mechanochromism is that we're not moving molecules around. We're actually breaking covalent bonds within the compound. So, this is, I think, a pretty interesting example of mechanochromic behavior of a transition metal compound. It's pretty rare. Okay, that's it. No more pictures. Thank you. I don't know if I've gone over. I apologize if I have. Thank you all. I want to thank my wife and my family. My wife is up there. She's going up. She's put up with me she was going to put this, so when I was 65, she was going to put this retirement party together for me. And I was too embarrassed to go to the retirement party, so I postponed things. My daughter Kim Balch Hammonds, my son Rudy Balch, my daughter Tamara Costello are both all here. And I also thank them for putting up with me. And I also thank them for the grandchildren that I have. Gwendolyn, Alexander, Lily, Abigail, Delilah, and Alistair. It's nice to be able to say this. Tomorrow, Abigail goes from Vermont to Arizona to her first scientific conference. And right now, Lily is in Lucca, Italy, attending a scientific conference, a Gordon conference, her first trip abroad. It's just nice to see my family at least taking up some of the science that I've done. I've shown you some of my students, certainly not all, and I apologize to those that I didn't get to talk about. They've all been wonderful. I've had lots of postdocs, lots of collaborators, funding from these agencies that have supported us, and I've been grateful for all of that. Well, thank you very much.
Yeah.
If I've gone too long, then let's move on.
No, it's the time is fine. So the debate here is that we're going to take questions or not. So if you have, please ask now.
Sarah, what was my favorite project?
Yes.
My favorite project was always the one I'm doing now. Yeah. But let's go to the way back.
Yeah.
The most exciting time in your career, scientific community.
I think when the
Can you
Fullerene,
repeat the question?
yeah, the question was, what was the most exciting time in my career? And I think the most exciting time was when the Fullerenes were discovered, and I got to be part of that. I mean, here's this round molecule. It's soluble, it's colored. I mean, it's got all the wonderful properties. And I wanted to be a part of it, and I got to be a part of it. And then there were just enormous number of papers coming out in that area, and it was just nice to be a part of. There was another question somewhere. Yes, yes,
That's fine.
that's fine.
My first question is, what do you define as like success in the scientific world? My second question was like, during your career, were there like any challenges you or your department had? And if so, like, could you share how have you navigated through that?
Okay, let's see. The first question was, yeah. Your first question was, give me your first question again. I'll repeat it.
How do you define success?
Oh, how do I define success?
Yes.
That's a tough question. I think success is getting a project to the point where we can talk about it and we can publish it. I think that's what I would say is success. And then there are levels of success. Some paper might get a lot of readers. It's more successful than paper that didn't. But success is getting it to a point where we can talk about it to other people. Now, you talked about problems, and the eternal problem to being a scientist these days is funding for your research. And that really, I found it difficult. I learned a lot from Gerd Lamar about how to write grant proposals. And I'm thankful for that experience, Gerd. But yeah, I would say that's the most difficult and challenging thing, other than being department chair. And I don't want to share that experience with you at all. Thank you for the question.
All right. What about a stand ovation to Alan? All right. Thank you, Alan.
Thank you.
Uh,
Thank you.
We need to collect your microphone. We are not over yet. We are not over yet. We have a brief remarks from the president of the UC Davis Emeriti Association, distinguished Professor Suad Joseph. Suad.
Thank you so much, Walter, for inviting me, and thank you, Professor Butter, for this amazing presentation. I came to Davis actually 6 years after you, in 1976, and I remember the hog barns and the pig barns, and we still have the cow barns. So the distinctive fragrances of Davis, you might say. I'm curious to ask your wonderful audience here, how many of you are emeriti? Could you just raise your hands? How many of you are emeriti? Only two. Okay, I'm going to be preaching to the audience. Okay, so I'm president of the UC Davis Emeriti Association. We have the Emeriti Association, our faculty, academic senate members who are retired. We have 1,500 of us from UC Davis alone, and tens of thousands more when you add all of the UC system. In fact, a few years ago, the system-wide Emeriti Association did a research of the continued research, teaching, and service that retired faculty have done after their retirement at UC Davis. And we discovered that there is enough research, teaching, and service that the emeriti do after retirement that they can constitute an 11th campus of the University of California. If you're interested in that, I have copies of the report. I'm also encouraging you to kind of pay attention to the things that we do. We are 400 members of the 1,500 join the Emeriti Association. We offer brain food talks, distinguished speakers to come and talk to us about their ongoing research. We have a meeting every second Thursday of the month in the Alumni Center, and we bring campus leaders to our to meet with us an hour before our meeting, deans and administrators and other campus leaders. We have one of the most amazing projects the Emeriti Association has conducted is under the leadership of Alan Jackman, who's over here. It's the Video Records Project. We capture our Emeriti and ask them to tell their stories, and we want to capture you and have you tell your story. And it's on videotape. We have done 540 of these. They are an amazing oral history of UC Davis. They're on the webpage. You can, they're actually on YouTube, a special page that you can get a link on from our website. We have a fundraising committee for the past 4 years. We have raised money for the Aggie Compass, focusing money for unhoused students. To my shock, I learned that 17% of the undergraduate students at UC Davis are unhoused. So we've raised money to help students. And we do regular programming throughout the year. So we just wanted to let you know that we are around. We'd welcome you to join us, whether you're emeriti or not, but certainly when you're emeriti. I have some brochures here if you're interested in. So contact us. We'd love to have you.
Thank you very much, Rod. I think this is a great opportunity for us to have a few minutes of an open mic. And I'm going to ask if anyone want to say something about Alan. And I'm going to volunteer Ella Jones. Would you please come forward and say a few words?
For those who don't know me, my name is Ella Jones, and my published name under Alan Balch was Ellen Fung. And so I was one of the few students that picked up the gold chemistry. And at the time that gold chemistry was not very popular because it's D10 metal, so it's colorless. And everybody else compound is bright orange, purple, you name it. And so my chemistry was boring at the time. And so until one day that I purified the compound, and somehow it just gave me the shot of light, and I got scared. I went to Alan and told him that something happened, and he came to the lab and observed the same thing that I saw, and that there is the birth of the sulfoluminescence. And I have to thank Alan for taking the risk to take me on as a graduate student. And some of the faculty members here knew at the time that I was at the bottom of my class. And so it is a real risk to take me on as a graduate student, not knowing I'm going to be a productive student or not. But Alan took the risk under his reign and trained me and taught me everything I know and mentored me over the years. And so I'm forever grateful to him. And he's a great mentor, and he's my academic father. And I am very glad to be here with great gratitude. Thank you.
Anyone else? David Britt, what about that? Would you come forward here, David?
Well, it's been a great honor to be here a while with Alan. I'm not an emeritus yet. And one of my early memories, kind of odd memories, is so I did my PhD at Berkeley in the so-called Melvin Calvin lab. I think I'd interviewed at Davis, and you probably don't remember this. All of a sudden, I would walk out of the Calvin lab, and there's Alan. So you were visiting Berkeley. I was very excited to see you. But I have to say, I think of a small group of faculty: Alan, Claude Mears, of course, Brian Miller at the time, Gert, and late Gus Mackey, who I don't think is mentioned today. Really responsible for bringing me to Davis, which I'll always be thankful for, because that was kind of a risk, because I have I have no degrees in chemistry. So I think Alan. Sure. Yes. Oh, it's okay. Thank you, Alan. I really appreciate it.
Thank you, Dave. Thank you, Dave. Anyone else? Anyone else would like to volunteer? If not, thank you very much for coming, but don't go away, because we're going to take a group photo in the back there. And where is the photographer, the official photographer? She's here somewhere, and she asked us to line up on the back there and take a photo. Thank you very much for coming, and thank you so much, Alan, for making UC Davis a better place.